have Karen Hsiang-Yi here today for the colloquium. Karen is actually my senpai. She was a few years ahead of me in NTHU physics. Back in college, I heard a lot about Karen, who was nicknamed Yang-Xiang at the time, about how good she was in class, and all very active in other activities as well. Obviously, it's not surprising that it only took her 1 year to finish her master. And she was moving to Illinois for her PhD. It was followed by a postdoc in Michigan, and then she was awarded a prestigious ASIAA fellowship at the Maryland. She recently come back at Tsinghua as a faculty, of course with the Hsiang-Yi Scholar Fellowship awarded. Karen is a world expert on feedback processes, in particular on the theoretical model side. And she recently made a breakthrough in understanding the Fermi bubbles. Now it's called Fermi eRosita bubbles. Is that right?
They're separate.
Separate bubbles, okay.
Yeah. They're different.
Right. So that made it to Nature Astronomy, which is a breakthrough. It's a renowned journal, and also caught attention to some public media. So today she'll be telling us more about the story. Karen, please.
Good afternoon, everyone, and it's really my great pleasure to be here, and thank TC for this nice introduction. So I'm Karen from National Tsinghua University, and today I'm going to share with you my 10-year journey of unveiling the origin of the Fermi and eRosita bubbles. So it's literally 10 years because the Fermi bubbles are two giant gamma ray bubbles discovered in 2010, revealed by the Fermi Space Telescope. And I published my first paper on modeling the Fermi bubbles in 2012. So this year is really my 10-year anniversary of modeling this gigantic bubbles in the Milky Way galaxy. So I'm going to share with you the story. Okay, so this is a work I've done in collaboration with Professor NTHU from University of Michigan and Alan Zweigel from University of Wisconsin, Madison. Okay. So the background picture here is our Milky Way galaxy, our home, our galaxy that we know and love. And actually a lot of great discoveries about the universe started right here. Okay? So for example, about 20 years ago, by using observations of stellar orbits around the galactic center, revealed the central supermassive black hole. And this is the really first firm detection by dynamical measurements of a supermassive black hole at the center of galaxy. And so this, of course, have won the Nobel Prize in Physics 2 years ago. And earlier this year, thanks to the Event Horizon team, we've also been able to image the central supermassive black hole. So Event Horizon telescope have tremendous resolution that allow us to really peek into the vicinity region around the central supermassive black hole. Okay, so this is the Sagittarius A star, the central supermassive black hole of 4 million solar masses at the center of our own Milky Way galaxy. And because that Sagittarius A star is the closest supermassive black hole in the whole universe, right? So we, by modeling and by observing its activities, we might be able to learn something about supermassive black holes in general. Unfortunately, Sagittarius A star at the present day has been really quiescent. Okay, so in terms of the antiton accretion rate, it's the least accreting supermassive black hole that we know of. All right, so for a long time, we thought that our Milky Way galaxy is just a normal spiral galaxy with nothing interesting happening. And therefore, it was a big surprise when the following discovery was made. So let me come back to this picture of our Milky Way galaxy. So this is the optical image that you are all very familiar with in the night sky. But now imagine that your eyes are gamma ray sensitive. Then what would you see? If our eyes can see gamma rays, actually this is what we will be observing. So these two gigantic bubbles are called the Fermi bubbles. The Fermi bubbles are two giant gamma ray bubbles revealed by the Gamma Ray Space Telescope in 2010. And its height is roughly 50 degrees above and below the galactic center. which corresponds to a physical scale of roughly 10 kiloparsecs. So it's really gigantic in physical units. And the width is about 40 degrees, and it's observed in the gamma ray waveband ranging from 1 to 100 GeV, and its integrated gamma ray luminosity is on the order of 4 times 10 to the 37 ergs per second, so it requires an enormous amount of energy to generate these bubbles. And these bubbles are symmetric about the galactic center, so it suggests that they must originate from some powerful outburst at the galactic center sometime in the past. Okay, so what kind of energy sources can produce this gigantic amount of energies? So first of all, because we know there's Sagittarius A star, so these bubbles could be due to some past activity from the Sagittarius A star. So an analog is the ASIAA jets that we observe in the Centaurus A system. Alternatively, you can also generate something looking like the Fermi bubbles, such as M82, which is a starburst galaxy. So by injecting a lot of energies from supernova remnants in these kind of starburst galaxies, you can also drive very large biconical outflows. Okay, so since the Fermi bubbles were discovered, actually it has been hotly debated which scenario is true, whether the Fermi bubbles are generated by some AGN-like activity or starburst activity. Okay, so let me show you the real image taken by the Fermi telescope here. So this image is what they observed after removing the galactic emission. Right. So because these Fermi bubbles are really close to us, it's only 8 kiloparsecs away, so we can really study them with unprecedented details and learn about the formation mechanisms of these gigantic bubbles. And in particular, by studying the Fermi bubbles, we may be able to understand various processes that goes on in our own nuclear galaxy and also other galaxies, including things like password transport, galactic magnetic field, galactic center activity, and learn about things like AGN feedback in general and starburst-driven activities, outflows in general. Okay, and in addition to the gamma ray, actually the vicinity of the Fermi bubbles is also observed in many other wavelengths, including X-ray, microwave, and even polarization measurements. So as you can see, these spatially resolved multi-wavelength observations really provides a lot of constraints in providing constraints on the formation mechanisms of these bubbles. Okay, so today let me focus on the X-ray sky. Okay, so this is the X-ray all-sky map taken by the ROSAT mission almost 20 years ago, and it's referring to the soft X-ray band. And this X-ray is coming from thermal branch-line emission of the gas within the galactic halo. So what you are seeing here on this map is the gas distribution within the galactic halo. And what you can see from this map is that it's really complicated. Okay, so the gas distribution within the Milky Way is really complicated. And one of the most prominent features on this map is this north polar spur, this arc feature extending to really high galactic latitudes. So this is the so-called north polar spur. And this north polar spur is coincident with a loop 1 feature in the radial band, which is related to a local superbubble in the solar neighborhood. Okay, so for a long time, many people think that the north polar spur in the X-ray sky is linked to a local structure in the solar neighborhood. However, in 2010, the Fermi bubbles were discovered, and if you overlay this contour indicating the location of the Fermi bubbles, you can see that this north polar spur seems to also be overlapping with the boundary of the Fermi bubbles. Okay, so now, then for the past few decades, people are arguing again about whether the north polar spur and these related arc features, whether they're related to a local event or a galactic center outburst. Okay, so this was the story before the eRosita mission was launched in 2019. Okay, so now After 2019, we actually have a much better view of the X-ray sky taken by the eRosita mission. Unfortunately, the eRosita mission is a joint Russian and German satellite, so it's currently suspended, so it cannot continue to take observations. But by accumulating the first few months of its data, it already reveals very striking structures in our Milky Way galaxy. So what you are looking at is a pair of bubbles, gigantic bubbles, extending to even like 80 degrees, even bigger than the size of the Fermi bubbles. So these are called the so-called eRosita bubbles. And because now we can clearly see the southern counterpart to the northern bubble, so now it is pretty obvious that at least some of the emission at the North Polar Spur should be related to a galactic center outburst. Okay, and because the morphology of these eRosita bubbles is very similar to the gamma ray Fermi bubbles, so it suggests that they may share the same origin. Okay, so this is the outline of my talk today. So first I will show you what do we know about the Fermi bubbles observationally. So I will go into these observations in more detail. And the second part is what do we know about the Fermi bubbles theoretically? In terms of theoretical modeling, how do we know how they originate? And what does the new eRosita data tell us about the origin of the bubbles? And then I'll discuss some of the interesting questions and implications of these results. Okay, so before we discuss about the physical origin of the Fermi bubbles, of course, we have to know the observational constraints. So let me go from one waveband to another. So first is the gamma ray emission. Okay, so in addition to its symmetry, which suggests a galactic center outburst, it actually has many unique features. For example, if you draw just a gamma ray intensity profile across the bubble surface, then you can notice that the Fermi bubbles have very flat intensity within the bubble, in the bubble interior, and they also have very sharp edges. Okay, so this actually tells us something about its property. For example, the flat intensity in gamma ray provides constraint on the 3D distribution of the cosmic rays that generate these gamma rays. Okay, so now assuming that you have a 3D distribution of cosmic rays that are spatially uniform, then after projection through a sphere, then you will get centrally brightened gamma ray intensity profile, right? On the other hand, if your cosmic rays are concentrated within a thin shell, then after projection, you will get limb brightening. Okay, so this flat intensity is actually non-trivial. Okay, so it tells us that the 3D distribution of cosmic rays cannot be totally uniform and cannot be concentrated in the thin shell. Okay, so it requires some very specific distribution. And the sharp edges also tell us something. So we know that cosmic rays, generally they can interact with the thermal gas in the medium and then gets diffusion. Okay, so cosmic rays can diffuse. So if you just apply the normal cosmic ray diffusion coefficient within the galaxy, then you should see very smooth transition from within the bubbles to the ambient region. However, what we observe is a very sharp boundary. So that suggests the cosmic ray diffusion process must be suppressed across the bubble surface. And probably the most significant constraints come from the spectrum. Okay, so here is a schematic diagram showing the gamma ray spectrum of the Fermi bubbles. So the purple line shows the gamma ray spectrum of the bubbles compared to other diffuse component in the gamma ray. And you can see that the bubble spectrum themselves are really hard. Okay, the spectral index is roughly -2, meaning that the gamma ray has to be generated by cosmic rays that have not had time to cool yet. Okay, so for example, we know that if these gamma rays are generated by cosmic ray electrons, which cool very easily due to synchrotron and inverse Compton cooling, then you should expect it to have an exponential cutoff pretty quickly if you don't inflate these bubbles fast enough. Okay, so basically the cooling time of these high energy cosmic rays gives us a very stringent constraint on the formation time of the bubbles to be within a few million years, if we assume the gamma rays come from cosmic electrons. Okay, so please keep that in mind because we'll come back to this point later in the talk. All right, so that's about the gamma ray sky. And later on, by accumulating more Fermi data, people have shown that actually you can divide these gamma ray photons into different latitude bands. And overall, the result is a confirmation of the previous result. And basically, the gamma ray spectrum can be well described by a parallel with spectral index of -2, and then having a high energy cutoff at around 110 GeV. And what's unique about this result is that the gamma ray spectrum seems to be very spatially uniform. Okay, so if you think about it, it's quite remarkable. Okay, the Fermi bubbles are really, really gigantic, right? It's really big. But this spectrum is telling us that no matter where you look within the bubbles, their spectra looks the same, roughly the same. Okay, so I'll also come back to this point later in my talk. So why is the gamma ray spectrum so spatially uniform? That's also a very interesting question. Okay, in microwave, we also observed some counterpart emission in the microwave band. So it was first detected by the WMAP mission and later confirmed by the Planck mission. So this residual emission in the microwave associated with the Fermi bubbles is called the microwave haze. And it's basically spatially uniform, spatially coincident with the gamma ray bubbles, and it also have very hard spectra. So it suggests that they may come from the same population of cosmic rays. And in general, the microwave comes from synchrotron emission. So basically, when you have cosmic rays, they interact with the magnetic field, produce this microwave emission. And so the gamma ray bubble is, if you look at its surface brightness, it's really uniform. But if you look at the profile of microwave emission as a function of radius away from the galactic center and compile this radial profile, it looks something like this. So it's centrally peaked. Okay, so this is basically due to the fact that the magnetic field strength within the galaxy is stronger near the galactic center and decaying away from the galactic center, which produces this centrally peaked profile in microwave band. Okay, so that's a microwave haze. And then coming back to the X-ray map. Okay, so this again is the original picture, all sky map taken by the ROSAT mission. And from this map already, we can say something about the Fermi bubbles. For example, if you look within the Fermi bubble region, then you see that it's not very bright in X-ray. Okay, so it suggests that these bubbles are underdense, so it has lower densities of thermal gas within the bubbles and higher densities near the edges. And also, we also see some arc features embracing the bubbles that's coincident with the bubble edges. So that can be due to compressed gas due to the shock that's driven by the energetic outburst. And in terms of TeV gamma ray, we also have some observational constraints coming from the Hawk Observatory. So the bottom panel shows the Hawk Observatory in Mexico. And here I'm showing you the GeV to TeV ranges compilation of the gamma ray spectrum. So this is the spectrum observed by the Fermi satellite. And these are the upper limits obtained by the Hawk mission above TeV ranges. Okay, so far, we don't detect anything associated with the gamma ray bubble in TeV waveband. Okay, so that puts very strong constraints on the theoretical models that try to explain the Fermi bubbles. For example, this red curve represents a hadronic model, which assumes that the gamma ray of the Fermi bubbles comes from cosmic protons. So if you assume that and assume that the cosmic protons have a parallel spectrum extending to PeV ranges, like what's shown in the red curve here, it's not consistent with the Hawk upper limits. Okay, so basically this Hawk upper limits tells us that purely hadronic models extending to PeV ranges are disfavored. Okay, so let me put all the observations together. And here's a schematic summary of all the observational constraints that we have. So the blue color represents the Fermi gamma ray bubbles. And at lower latitude, we observe the microwave haze. Yeah, that's in microwave band due to synchrotron emission. And the ROSAT map shows that the Fermi bubbles are embraced by these X-ray arcs near the bubble edges. And now with the newly launched eRosita mission, that we can see a more extended eRosita bubble extending to even 80 degrees above and below the galactic center. And so far, we have not found any associated with detections in TeV waveband yet. Okay, so since the discovery of the Fermi bubbles, actually many theories have been proposed to explain all these data. But as you can see, with this level of details, it's actually very challenging for any theoretical models to reproduce all the multi-wavelength observational data. Okay, so now let's try to ask the question of what is the origin of these bubbles. Okay, so in terms of theoretical modeling, what people are concerned with are the following three questions. The first question is, what are the emission mechanisms? So it can be either leptonic, meaning that the gamma rays are caused by cosmic electrons when they interact with the interstellar radiation field in the galaxy. So in the galaxy, you have low energy photons from starlight or CMB photons, for example. They can be inverse Compton scattered by the cosmic electrons within the bubbles and produce gamma rays. And these cosmic rays can also gyrate around magnetic field lines, producing synchrotron emission that shine in the microwave band. Okay, so that in terms of the leptonic scenario, these are the mechanisms that can produce the gamma rays. Alternatively, you can also have hadronic interactions producing gamma rays. So when you have cosmic protons within the Fermi bubbles, they can collide with ambient protons in the interstellar medium and producing these so-called PP collisions or hadronic collisions. And then the product of the neutral pion will then decay into gamma rays. And another channel produces charged pions, which will then further decay into muons and then secondary electrons and positrons. And these secondary particles can then gyrate around magnetic field lines and produce microwave haze emission due to synchrotron emission. Okay, so in terms of the emission mechanism, these are the two possible mechanisms that can produce the gamma ray. And the second question that we're interested in is what activity at the galactic center triggers the event? Is it due to nuclear starburst or AGN activity? And the third question people want to know about is where are the cosmic rays produced? It can be either produced very close to the galactic center and transported outwards to large distances, or it can be in situ accelerated by shocks or turbulence near the bubble surface. Okay, so note that actually not any of these combinations will work. It's because we have the constraints coming from the very hard spectrum in gamma ray. Okay, so let me try to elaborate a little more. So now say if you want to come up with a model that's based on starburst wind, then because these winds typically travels at hundreds of kilometers per second, so it will take more than 10 million years for these winds to transport these cosmic rays to large distances. Okay, so it takes more than 10 million years to transport these cosmic rays by wind. And therefore, the gamma ray emission in this case must be hadronic. Okay, otherwise the cosmic electrons would have cooled. Okay, so this is the first category of models called hadronic wind models. And say if instead you want to build a model based on leptonic emission, then what you need is something like the AGN jets, which can transport these cosmic rays very fast, very quickly, before the cosmic electrons cool. Okay, so this is the second category of the models called leptonic jet models. And alternatively, you can bypass all the age constraints and by invoking in situ acceleration of cosmic rays near the bubble surface by shocks or turbulence. And in this case, you don't need to care about the triggering event. You just need to have a shock that can produce the cosmic rays that you need. All right, so like I said, many theories have been proposed to explain the formation of the Fermi bubbles, but any of these models have to fall into one of these categories. So in the following, I'm going to just summarize the important findings for each category of the models. Okay, so first is the hadronic wind models. So like I said, in this kind of hadronic wind models, they invoke winds that can travel at a speed roughly hundreds to 1,000 kilometers per second. And because typically starburst winds or avian winds, they are more spherical, so it needs to be collimated by something like the central molecular zone. And so for these wind models, you can use starburst wind or avian winds. So both are possible. So here I'm showing you some examples from previous studies. And in general, what's found in this previous work is that the hadronic wind model can produce the gamma ray properties of the Fermi bubbles quite well. Okay, so actually the main challenge of this hadronic wind model is its microwave haze emission. Okay, so in terms of predicting the microwave haze, for the hadronic case, remember we have the secondary particles that can gyrate around magnetic field and producing the synchrotron emission. So if you do that calculation for the secondary particles, then what's found is that actually the predicted microwave emission is not enough for these hadronic wind models to reproduce the microwave haze emission. So overall, they don't produce enough microwave haze emission compared to the observational data. So these curves represents the predicted spectrum from the hadronic model, from the secondary particles. And even if you normalize the predicted spectrum with the observed amplitude, like this one, so it's the renormalized spectrum at roughly the microwave haze frequency, then you can see that the predicted spectrum is much softer than the observed one. Okay, so it means that actually in this hadronic model, the predicted secondary microwave emission failed to reproduce the observed microwave haze data. Okay, so that is the first drawback of the hadronic wind model. And the second drawback is that, like I said earlier, it fails to explain the upper limits provided by the Hawk Observatory in the TeV band. Okay, so overall, summing up from all these previous works, it suggests that the purely hadronic models are disfavored as the formation mechanism of the Fermi bubbles. Okay, so we basically ruled out the first category. So let's talk about the leptonic jet model, the second category, which I've been working on for the past 10 years. Okay, so like I said, in this kind of leptonic jet models, we require jets of very high speed to transport these cosmic rays very quickly. So the typical initial speed invoked of the AGN jets is on the order of thousands to 10,000 kilometers per second, so that we can inflate these bubbles within a few minute years before the cosmic electrons cool. And overall, by my work and others' work, we found that both the Fermi bubble and the microwave haze can be well reproduced by the same population of cosmic electrons. So that's a very good advantage of this leptonic model. Okay, so let me talk a little more about the gamma ray spectrum of the leptonic jet model. So like I mentioned earlier, the newer Fermi data revealed that when you compile the gamma ray spectrum for different latitude bands, it's actually very, very spatially uniform. Okay, so it's well described by a power law and a high energy cutoff, and everything is very spatially uniform. But that's really weird if you think about it. Okay, so the high energy cutoff is generally what you might expect for a leptonic model, because cosmic electrons cool very easily, so you easily get an exponential cutoff. However, even for the leptonic jet model, it's not clear. It's not obvious why the gamma ray spectrum should be spatially uniform. Okay, so in order to understand this, I implemented a custom ray spectral evolution code into Flash, which is the MHD code. So we implement this code to track the evolution of custom ray spectra on the fly during the MHD simulations. And so we use that to simulate the evolution of leptonic AGN jets injecting from the galactic center. And we assume that all the custom rays associated with the AGN jets are leptonic, so it contains custom ray electrons. And the initial injected spectrum ranges from 10 GeV to 10 TeV with a spectral index of -2.1. And in the simulation, we can then evolve this custom ray spectrum due to inverse Compton and synchrotron cooling self-consistently. So by modeling the inverse Compton scattering, we use the Galactic's interstellar radiation field. And by calculating the synchrotron emission, we use the Galactic's default magnetic field distribution. Okay, so here I show you some of the slices during the simulation. So normally when people put in custom rays, they just put in a single component and modeling the total energy density of the custom rays. But now by modeling each custom rays of different energy bands, we can then divide them into different energy bands and calculate their corresponding emissions. Okay, so we can use this code to very conveniently and self-consistently compute the non-thermal emission that we expect predicted from our simulations. Okay, so what do we get? So in terms of this kind of custom ray spectral evolution modeling, this is the result of our simulation. So this is the simulated gamma ray spectra. Again, the different colors corresponds to different latitude bands. So overall, we find very good agreement with the spatial data. We find that the gamma ray spectrum is very, very spatially uniform, latitude independent, and it all has a very also spatially uniform high energy cutoff at around 100 GeV. Okay, so how do we understand this result? So basically, what we found is that this high energy cutoff, the energy of this maximum energy of custom rays is essentially set at the very beginning when the jets were first launched. So when the jets were first launched, it suffered from very fast synchrotron and inverse Compton cooling, so that the parallel spectrum already have an exponential cutoff at early times. And later on, after the jets leave the galactic plane, basically the dynamical time of the jet becomes the shortest time scale among all other cooling time scale, and therefore the spectrum just be transported to large distances without changing its shape. Okay, so when we plot the maximum energy of the custom rays in our simulation, we can find that basically the energy of these custom rays are very spatially uniform, and that's because they all retain the memory from the time when they were injected at the galactic center where they suffer fast cooling. Okay, so this is, I think, a very neat explanation of why the Fermi bubble spectrum is so spatially uniform. And this idea is actually very analogous to the idea of inflation, when, where the isotropy of the C and B can be explained because when you invoke inflation, they all started from some small region with causal contact. Okay, so this idea is very analogous to how we use the leptonic jet model to explain the spatially uniform spectrum of the Fermi bubbles. Okay, so overall, we find that the leptonic jet model works quite well. So how about the third category? The third category is the so-called in situ acceleration models. So I don't have much time, so I won't go into much detail. But basically, they invoke custom rays that are accelerated near the shock due to shock acceleration and also turbulent acceleration in the shock downstream. Okay, so for example, a recent work by Merchant et al. 2018, they assume that shocks are generated by some event. So they don't specify the event. It can be either due to AGN or starburst activity, and assume that the customer electrons are injected at the shock and accelerated by turbulence in the shock downstream. And they found that the spatially uniform gamma ray spectrum and microwave haze can also be reproduced. Okay, but they have to assume certain magnetic field geometry and customer diffusion coefficient, etc. Okay, so it's not fully self-consistent, but they can also map the observational data quite well. Okay, so I believe a question that you may have is then whether leptonic jet model or in situ acceleration model is true, right? Which model is true? So it seems that both models works quite well in terms of explaining the gamma ray emission and its properties. So let me come back to this cartoon picture again, comparing the leptonic jet scenario and the in situ acceleration models. Okay, so like I said, in terms of predicting the non-thermal emission, the gamma ray and microwave bands, they perform equally well. Okay, so what are their differences? There's actually one key difference between these two models, which is the location of the shocks. Okay, so for example, for the in situ acceleration model, it is assumed that the customer is generating the Fermi bubbles are accelerated by shocks and turbulence in the shock downstream. So by construction, the shock surface, the location of the shocks, has to be coincident with the edge of the Fermi bubbles. Okay, so by assumption, by construction, we should see this. The shock surface should be coincident with the boundary of the gamma ray bubbles. On the other hand, for the leptonic jet model, in general, when you have an energetic outburst, the forward shock can go to much extended distance away from the galactic center compared to the contact discontinuity between the jet material and the shocked ambient material. Okay, so this is generally the configuration of the leptonic jet material where we expect to see the shocks much further away from the surface of the Fermi bubbles. Okay, so the key to distinguish these two scenarios is to look for the shock. So how can we find the shock? We can, again, go back to the X-ray sky, right? So here I'm showing you the ROSAT all-sky map again. So by looking at this ROSAT map, as I showed you earlier, there seems to be some arc features embracing the bubbles. But because the ROSAT mission has limited sensitivity, so we can not really tell whether these arc features are coincident with the bubble surface or not, right? However, now with the new eRosita data, things have changed. Okay, so now with higher sensitivity, we can more clearly see the boundary of the X-ray bubble. Okay, so if we overlay these two bands together, then here's a very beautiful and striking image overlaying the X-ray bubbles in cyan and the gamma ray bubbles in red. And from this picture, it's not only beautiful, but it tells us something, that these two surfaces are not the same. Okay, so they are not coincident with each other, which tells us that the more likely interpretation of the result is that the eRosita bubble represents the forward shock of the energy injection, and the Fermi bubbles represents the contact discontinuity between the jet material and the shocked ambient medium. Okay, so when I saw this picture from the eRosita map in the end of 2020, I was really, really excited because this map tells us that the leptonic jet model could be true. Okay, so I was really excited, and I was going back to my earlier simulations, and I tried to find a parameter set that can reproduce both the location of the Fermi bubbles and the location of the shock front. And I successfully found one. Okay, so here I'm showing you a simple animation made from my revised simulations. So here I'm showing you the animations of bubble formation caused by AGN jet injection near the galactic center. And here in the simulation, again, we are modeling both the cosmic rays and the thermal gas. And the cosmic rays are shown by these red and white contours. So this marks the 3D distribution of the cosmic rays within the simulations. And again, in the simulation, we can model the cosmic ray spectrum self-consistently, including synchrotron and inverse Compton cooling, etc. So we can compute the gamma ray emission and microwave emission, etc. And in the simulation, we can also model the evolution of the thermal gas that's interacting with the cosmic rays. So here in the cyan color, what you can see is the shock front that's propagating outwards due to the energy outburst near the galactic center. Okay, so what about the results? So here I'm showing you that the compilation from our simulated data. So this is an overlaid image predicted from our simulation of the X-ray emission and the gamma ray emission in red. Okay, so overall, we find that the overall morphology of both the gamma ray bubble and the X-ray bubble are reproduced very well in the model. And on the bottom left here, I'm showing you the broadband spectrum predicted from our model, and we can see that, okay, the spectrum also matches with the observed microwave haze data, Fermi bubble data very well, and it's also consistent with the Hawk upper limits. And on the bottom right here, I'm showing you the profile, so spatial distribution in microwave and gamma ray. So overall, from our simulation, we also predict a centrally peaked profile for the microwave haze, and also we obtain the roughly flat intensity map across the bubbles, within the bubbles for the gamma ray band. Okay, so overall, we find that all the multi-wavelength data, including the spectra, are well reproduced by this lactonic jet model. And this has been published in Nature Astronomy earlier this year, and it has been also featured on many public and scientific media. So if you're interested in this work, feel free to read more about these. And so what can we learn from our simulations? So we can guess a few important constraints. For example, what we learned from our simulations includes the following. So the jets occurred roughly 2.6 million years ago, and they were active for a very short period of amount of time, roughly 0.1 million years. And the inferred Eddington ratio, the energy required to infer this bubble is quite large. So the Eddington ratio at the time of its active period is around 1 to 10%. And interestingly, these kind of timescales and energetics that's inferred from modeling the Fermi bubbles and these multi-wavelength structures is consistent with another independent measurement of ionization cone in the Magellanic String. Okay, so this is a series of work done by Blunt, Hawthorne et al. 2013 and 19. So they basically found that there's an enhanced H-alpha carbon and silicon line ratios, suggesting that the Sagittarius A star might have a past Seyfert flare activity before. So basically, when they look at the ionization signatures in the Magellanic Stream, they found that along the North Galactic pole, actually there's enhanced ionization signatures. So it cannot be really explained by other sources of ionization, but what they found is that it's more consistent with the past Seyfert-like activity of the Sagittarius A star. And they model this ionization signature, and this is their inferred activity level. So again, they found that the Eddington ratio of Sagittarius A star is roughly 1 to 10%, and the age of this ionization event also occurred roughly 3 million years ago. Okay, so both modeling the multi-wavelength bubble spectrum tells us that the Sagittarius A star has some activity a few million years ago, and here is another independent constraint telling us you could have such Seyfert-like activity before. Okay, so now I hope I convinced you that our Sagittarius A star might not be just a really normal and boring black hole, but it actually has some interesting activity a few million years ago. So I'm going to show you some results and discuss some of the interesting questions coming out from this study. For example, we can start to ask whether we can observe something like the Fermi bubbles in nearby galaxies, right? So in a recent work that's led by Alice Owen, a Sgr A fellow at NTHU, we modeled the multi-wavelength spectrum from aging galaxy bubbles similar to the Fermi bubbles. So basically, we ran our simulations for longer, and we compared the leptonic emission and hadronic emission in broadband, in terms of this broadband spectrum. So here I'm showing you the leptonic scenario. So this is the predicted leptonic spectra from our first work. So here I'm showing you the spectrum and its evolution. So basically what we found is that because in the leptonic jet model, the cosmic electrons, again, cool very easily. So in terms of the high energy emission in GeV and TeV, they die out very quickly. So even if you have a very sensitive telescope like CTA in the future, only a few would be observable because Fermi bubbles are really faint objects. So yeah, so we might be able to see a few, but not many. On the other hand, in the radio band, it's more promising because the radio emission drops relatively slowly. So given sensitivity like the Sgr A in the upcoming few years, we could observe maybe to a few dozens. Okay, so this is one aspect of trying to observe Fermi bubble-like analogs in nearby galaxy. And another interesting question that we can ask, and I was asked by many people, is what about the jet inclination angle? So in my previous simulations, I've always assumed that the jet just goes perpendicular to the galactic plane because we observe the Fermi bubbles and they are very symmetric, right? So that is the basic assumption in our model. But many people don't like it, right? Because it requires some fine tuning and it seems to be too coincidental, right? And in general, if you look at AGN jets in other galaxies, then they generally do not have to align with the rotational axis of the galactic galaxy, right? For example, in Centaurus A system, the jet is also tilted, and in general, the AGN jet direction is related to the black hole spin axis, which is determined by physics that's very close to the supermassive black hole. So it can have nothing to do with the large-scale galactic plane, right? So in general, we normally do not expect the jets to be totally perpendicular to the galactic plane. So that's one motivation to consider a different jet inclination. And another motivation is coming from this very nice work from the EHT team. So basically from the black hole shadow image of the Sagittarius A star, they ran a bunch of different GRMHD simulations with different parameters. And what was found was that actually they can get the constraints on the spin axis of the Sagittarius A star at the present day, right? And what they found is that the Sagittarius A star is very likely to be pointing at us. Okay? So these interesting constraints tell us that, okay, the black hole spin axis could be pointing at us. So what if it shoot out a jet a few million years ago, right? Of course, the spin axis of the black hole does not need to be the same at the present day versus a few million years ago, but it's an interesting question to ask whether we can release the constraint about the jet inclination angle in our modeling. Okay, so that is why we performed another study on this work. So what we want to ask is, can tilted jets produce symmetric Fermi and eRosita bubbles? So this is a work led by Dr. Guoxun Zhen, NTHU and Lanhai. So what we use is the 3D spatial relativistic hydrodynamic simulations using the Gamma code developed by him. And what we model in these simulations is tilted jet interacting with a clumpy galactic disk. So here I'm showing you the initial conditions for this new set of simulations, including its initial pressure, temperature distribution, and gas density distribution. And we put in a jet that's inclined roughly 45 degrees away from the rotational axis of the galaxy. And so what do we find? What do we find? Here I'm showing you the results of the temperature distribution and density distribution at a time that's roughly 12 million years. So on the left-hand side is a simulation with a clumped disk. So basically what we found is that if you just put in tilted jet after interaction with the dense disk, then it can have enough randomization so that when the jet comes out, it actually drives outflows perpendicular to the galactic plane, producing roughly symmetric bubble structures looking like the Fermi bubbles and eRosita bubbles. And we also test another case where we don't put in any galactic disks at all. And in that case, basically, the jet just pumps through and producing these asymmetric structures that's inconsistent with the observational data. So by doing this experiment, we know that putting in a dense disk is very important, and we require to have that disk to interact with the tilted jet and produce a more symmetry structure of the bubbles. Okay, and what about the observational signatures? So we also made some predictions about the X-ray map, the gamma ray map, and the spectrum in microwave and gamma ray. And we find that basically this tilted jet model can also reproduce the morphology of the Fermi bubble and eRosita bubble. And so in this simulation, we have not modeled the cosmic spectra self-consistently yet. So we just put in a uniform cosmic spectrum with a power law index of minus 2.4. We just put in by hand, and it seems that the microwave spectrum and the gamma ray spectrum is matched quite well also. Okay, so overall we find that this tilted jet model is plausible. However, one drawback of this model is that when you take a look at the formation time, it's about 12 million years. It's longer than the cooling time of cosmic electrons. Okay, so it means that if we model the cooling of cosmic electrons self-consistently, then we will not be able to reproduce the hard spectrum that we observe, that we require. Okay, so it suggests that this longer formation time requires some cosmic reacceleration within the bubbles. So during the inflation of the bubbles, we require the cosmos to be reaccelerated, possibly due to turbulence. Okay, so overall, this new work of a tilted jet suggests that, okay, this model could work, but we still need to explain why there's some turbulence reacceleration and why this kind of reacceleration can produce spatially uniform cosmic spectrum with the index of minus 2.4. Okay, so we still need to address that in order for this tilted jet model to work. Okay, so the bottom line is that if you just take it as an assumption that the jet goes in the perpendicular direction, then everything can be fit very nicely. But if you don't like that assumption and you want to invoke tilted jet, then we still need to explain where the cosmos are accelerated. Okay, so in summary, I showed you in this talk that the multi-wavelength observation of the Fermi and eRosita bubbles are likely caused by a single outburst of jet activity of the Sgr A star, and the inferred age of 2.6 million years and the Eddington ratio roughly 1 to 10% are consistent with enhanced ionization structure in the Magellanic String, pointing to a Seyfert flare activity of the Sgr A star. And many open questions remain, so I've discussed some of them, but particularly, what this Fermi bubble is telling us is that the AGN jets do not only affect those higher mass systems like elliptical galaxies and galaxy clusters, where we think AGN feedbacks are really important, But jet feedback can also occur in normal galaxies like the Milky Way. Okay, so what do they do? So is AGN feedback important in Milky Way-like systems? And how does this event, this particular event, link to the overall picture of supermassive black hole and galaxy co-evolution is what I will be interested in addressing in the future. Okay, and finally, let me just give a little advertisement here. So the NHG plus cosmic spectral evolution code is a very powerful tool, not only for modeling the Fermi bubbles, but it can be also applied to other interesting astrophysical systems to model their thermal and non-thermal emission, including things like galactic winds, cluster radial halos, other AGNs, and supernova remnants. So if you think your favorite systems also can have significant contribution from cosmic rays, and if you're interested in modeling them and calculating their spectrum, etc., I'll be very happy to talk with you. Okay, I'll stop my talk here. Thank you very much.
We can have a few questions, please.
Fascinating. Now, in the eRosita data, what temperature and density do you infer for that shock?
Right. So from our simulation, the shock immediately post-shock temperature is actually very high. So it's around a few times 10 to the 8th Kelvin.
The tens of keV.
Yeah.
But
yeah.
okay, so in the eRosita band, you just see the low energy part.
Right.
What about N? What's the N?
Right. Let me try to recall. It's maybe on the order of 10 to the minus 2 cubic per cubic centimeter.
10 minus
for the N.
2.
Yeah.
So in that picture,
Because it's already pretty high latitude. So there, the galactic halo, the original gas density of the galactic halo.
I'm not talking about the theory.
Yeah.
The flux,
Yeah.
you know the density,
Right.
the measurement, not the theory.
Oh, okay. You mean from the constraints?
It was just the flux, right? So you know that emissivity epsilon n squared t to the 1/2. You know t.
Yes.
You know epsilon. You know the flux, so you know n.
Right.
You measure n. You know what that is?
Let me try to maybe read it from. This plot? Oh, sorry, I didn't show the X-ray. Okay.
No, because again, this has a big implication because the different models for the halo gas differ by a factor of 1,000 in NE. Okay, so what you assume makes a big difference.
Oh yeah,
Or what
but
we'll see.
we actually do have some constraints on the gas density profile from absorption line studies.
Well, but those are highly controversial in my opinion.
But yeah, that's the best measurement that we have.
But that's why I'm thinking this is a good way of measuring it. I mean, nothing beats the measurement because in X-rays, you actually measure n
Right.
fairly robustly if in that interpretation.
So yeah, from our simulation and comparison with the observational data, it seems quite consistent with that model. Okay, so based on absorption lines, they get the beta model profile, and then we put that in as the initial condition, and we invoke the shock. And the shock is really high Mach number, so it only increases the local number density by a factor of 4, roughly. So and we can reproduce the eRosita emission. So it means that
beta model you could assume it RC. I would say that's uncertain by a factor of 10.
Yeah. It's very uncertain, but it seems to be right at the ballpark.
Right meaning what's the right number? 10 kiloparsecs or 100 kiloparsecs?
Sorry.
I'm just saying in the beta model, there's this free parameter called RC.
Yeah.
And some people will say it's 1 kiloparsec, some people will say it's 100 kiloparsecs.
Yeah.
What number do you pick?
I don't have that number off the top of my head, but yeah, we use the Miller and Bregman measurements as the initial condition. Right.
So back 50 years ago, and what was studying the North Polar spur is also called loop 1. Okay, it was believed that it really is a big shell.
Yeah.
It's a big local phenomenon. And the ionizing source inside is the Sgr-A association. So Sgr-A, this OB association, its age will be a few million years. So the ionization for this imaginary stream could very be provided by the School and Open Association. I don't know if Glenn Hawthorne discussed this. And because all these ionized gas, those ions, they can be easily photoionized by all these stars. So it does not require, it's hard for me to imagine you have a flash, a jet or whatever, and can photoionize. It's not photoionization, is it collision ionization or what?
Photoionized actually.
Is photoionization?
Yeah, but I think in their modeling they tried different sources and they concluded that only AGN-like activity is enough to have such a
But the
enhancement.
is still alive. It's still open association. It still has stars.
Yeah, so from that ionization sources, do we expect to see only the cone, or do we expect to see a more broadly distributed enhancement?
I should know this magnetic stream, how far, how widespread it is in the.
Yeah. This is sort of what I guess. Yeah. The opening angle is maybe
See,
30 degrees or something.
50 years ago, we all think these loops are all very local phenomena. Within a few hundred parsecs.
Yeah, indeed. Yeah. Right. Indeed. Before the discovery of the eRosita bubble. Yeah.
Also has each one counterpart. So your model did not take into account that each one at all.
Oh no, we don't model actually because they are really low temperature. Yeah, we cannot model.
Squeeze H1 to accelerate H1 to this, to kind of shell structure. That requires different magnitude.
Right. Yeah, and these cold clouds are extremely difficult to model in any simulation. So yeah, we don't plan to do that. Yeah, it's not easy to put them in.
No, but those cold clouds are nearby. I mean, you're talking about things 10 kiloparsecs away. So I think you would say that the cold clouds are unrelated to the eRosita, but you just say that. I mean, we know there's a local bubble. We know that this polar spur is local. But you're saying the eRosita is something at 10 kiloparsecs away, whereas we know the 21 centimeter the cold gas is not 10 kiloparsecs away. So in her model, these two are unrelated, I think.
Right. Yeah.
Patrick is in it. Patrick, of course.
Is it clear that this is a single event, or could it be accumulation of episodic outbursts from the paradise star?
It's a very good question. So, of course, in terms of modeling them, we want to see if a single injection can explain the phenomena, and it does. So I would say this is the simplest model that can explain the gigantic eRosita and Fermi bubble. And the Sgr A star actually has some past activity, so on different timescales actually. So people study, for example, reflection nebulae around the galactic center region, and they can put constraints on various different levels of activities on different timescales. So actually, we know that the Sgr A star activity has been episodic. Just that the Fermi bubbles and eRosita bubbles require really high energy injection, which is very different from the other activities. Right.
In your the later tilted jet simulation, the
Right.
time scale is longer. So
Yeah.
is that just due to geometric effect, or this is because of the dense material that's slowing down?
Yeah, exactly.
The
So
second.
it takes some time for the jet to interact with the galactic disk, and then it slows down a bit, and therefore the outflow it drives is actually slower, so it takes longer time to reach the same height.
So in the original modeling you have in the current paper, does that also include the dense material?
No.
So the time scale, if there's dense material, it would also be longer.
So the jet parameters is actually a little different. Okay, so we don't put in the disk, so you can think that what we put in the current model is sort of the parameter after the jet already interact with the galactic disk. Okay, so that's what we put in as the initial condition. So, right.
And in this particular event, how much mass you might need to dump to
Yeah. So at 1 to 10% of emitton, it has to eat roughly 10 to 3 to 4 solar masses.
Can this event happen again then? Can this happen again? Like, it was not long ago, 3.5 million years old. Is it possible or likely with the current conditions in the galactic center for it yet to emerge again?
You mean, could it happen again?
Yes.
Maybe.
But I mean, do we know enough about the conditions around the galactic center to predict if this could happen or might not happen?
I would say that based on its current activity, it's extremely low. So the current emission ratio of Sagittarius stars is on the order of 10 to the minus 9 or something. Yeah. And therefore, it seems like currently it doesn't have enough material to accrete.
Well, no, I'd say there's a lot of material, it's just not
Yeah,
accreting.
it's not dumping.
So there's plenty of mass. I mean, 10 to the 3 solar masses is nothing. That's a million.
It just needs some instabilities or something to happen to like immediately have a surge of mass onto the black hole.
Okay, thank you.
Right.
Last one. Go ahead.
I just wanted to ask, how did you calculate the inverse age of the jets? Right? Was it from the perpendicular model?
Right, so we can basically, in our simulations, vary a few different combinations of jet parameters. And from the injection to the time when the bubble edges reaches the observed one, that's the age
So
that we get.
in the tilted models, the inferred age was actually much longer, right?
Right.
About 12.4 million years. So have you tried like slightly less tilted since you said it was about 45 degrees?
Right. We also tried different inclination angles, but it's not short enough to be shorter than the cooling time. Right, so no matter what angle you use, you still need to invoke some reacceleration.
Can I ask what the cooling time is? Is it around 2.6 million years?
Right. So it's roughly on the order of 3 million years for 1 TeV cosmic electrons.
I see. Thank you.
Well, isn't it just the case that if you're moving at 10,000 kilometers per second, you just don't care what the
Right,
ISM is
right.
doing,
Yeah.
and then the angle doesn't matter.
Right.
So it's got to be slow for the angle to matter.
Yeah. Exactly.
All right, I think time's up. So let's thank Karen again.